Hello, this is Dr. Donna Burnett. Today we're talking about the chemistry of food composition. Let's get started. Chapter objectives. By the end of this chapter, you should be able to explain the compositions and functions of the 6 nutrient groups, give examples of the role of water in food, describe the chemical structure of carbohydrates, lipids, and proteins, provide the food sources and functions of carbohydrates, lipids, and protein, list the main vitamins and minerals found in foods, and define several non-nutrient substances that are found in food, especially food additives. Let's start with basic food chemistry. The 6 nutrient groups are carbohydrate, protein, lipids, vitamins, minerals, and water. These are the 6 classes of nutrients that you will hear in any nutrition class. It's the very basic way that we organize the composition of food. All foods consist of one or more of 6 key atoms: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. 6 nutrient groups in food and people are depicted on the right in figure 3-1. If you'll notice in figure 3-2, the body is composed of approximately 60 to 70% water, 15 to 25% fat, which varies by gender and also just overall body weight, body composition, fitness level, 15% protein, and 12% minerals. What is missing here would be what? Carbohydrate and vitamins. And that's because the body does not store carbohydrate or vitamins in a large enough quantity to even show up on this chart. They're there, and as we will discuss, they're in smaller quantities. The water content in foods varies widely from 0% in oil all the way up to 93% plus in tomatoes. So you can probably get a good idea of the water content in foods by even how it tastes and if it's juicy or if it's dry, if it's dehydrated, if it's sticky. But it is good to know the actual percentages. This will also help determine the caloric content of the food. Obviously, the more water, the less dense the caloric value. Now, that explains why oil and fats in general are the highest caloric value food group density. Okay, so fruits and vegetables generally will be 70 to 95% water. Whole milk is 80% water, and you have to account for the fat and the milk solids that are in there. You notice on the chart it says 87%, but we also have to think about skim milk and low fat milk. Most of your meats will average just under 70% water. On the least amount of water will be found, as I mentioned, in oils, also dried foods. Water is the simplest of all nutrients. We have one atom of oxygen flanked by 2 atoms of hydrogen. You'll notice the charges on there. This creates a dipolar molecule. Water can be used as a standard in several different processes, but one process would be calorimetry. 1 kilocalorie, which is what we use to talk about calories in food, equals the energy needed to raise 1 kilogram of water by 1 degree Celsius at normal pressure. This is the baseline for comparing other materials, with 1 calorie heating 1 gram of water by 1 degree centigrade. Here you have your 3 states of water. You have ice, which is solid and has molecules lined up closely together. You have liquid water, which we just call water, and then we have it in a gas form, which is steam. And you'll notice that in water, water molecules move away from each other but do not escape, whereas in steam or gas, they move so far apart they escape into the air. Water differs from other compounds in the amount of energy it takes to reach a specific freezing, melting, and boiling point. So the freezing point is the temperature at which a liquid changes to a solid, and water freezes at 32 degrees Fahrenheit. If you add salt or sugar or other solutes, you can lower the freezing point of water. A solute is a solid, liquid, or gas compound dissolved in another substance. This is a key principle in food science. Not everything will dissolve. The melting point is the temperature at which a solid changes to a liquid. The boiling point is the temperature at which a heated liquid begins to boil and changes to a gas. The critical point here is the boiling point of water at sea level is 212 degrees Fahrenheit, but as you increase in elevation, you decrease the boiling point of water. There's less atmospheric pressure on the water at higher elevations. Heat of vaporization is the amount of heat required to convert a liquid to a gas. These are just terms that you need to know. Hard water versus soft water. You may know this from the area where you live, whether you have hard water or soft water. Hard water will have more calcium and magnesium, while soft water is higher in sodium. Functions of water in food. These are very important in food science. One main function of water is to transfer heat in the cooking process. Another is to work as a solvent. You know, water is the universal solvent. And water functions in food as a solvent in food preparation. It plays a key role in chemical reactions, and it's an important factor when we talk about food perishability and preservation. Here's a table 3-1, that goes over the functional properties of food, of water in food, as we just discussed. You will have a solution, you can have a colloidal dispersion or a coarse dispersion, which is a suspension. We'll talk about those in the next slide, but also note that the heat transfer, which is what you're probably most thinking of, is boiling, simmering, steaming, stewing, and braising. We will discuss that at length in food preparation lectures. The solvent we'll talk about in a few minutes. And then also you'll see water functioning and chemical reactions. Table 3-2 talks about the different types of dispersion. So you have a solution when the solute is small enough, and that would be like sugar and water. Think of making iced tea with sugar, sweetened iced tea. Um, an example, alcoholic beverages when you're mixing solutions. Same with gas. When you get a little bit bigger particles, you can have a dispersion, like in gravies or jellies or egg custard. You have emulsions, which are huge in food preparation. We'll talk about that. That's a big food science topic. And you have foams, again, very big topic in food science. Then if you have large particles, you call it a suspension, where you have one um, one content suspended in another type of content. Example, cornstarch in water. So we suspend the cornstarch in water long enough to, if we're going to use it to thicken something, to incorporate it in that dish. Figure 3-7 talks about what happens when a dispersion is destabilized. So we just talked about how dis- solutions, dispersions, and suspensions form, but they won't stay that way forever. Um, Sometimes you'll have creaming where um, let's take an example of whole milk. You're churning it to make butter. The fat comes out of the dispersion and forms at the top, and you have cream rises to the top. That's where that expression comes from. You can have sedimentation where the dispersion breaks down and you have the sediment um, migrating to the bottom. You could have coalescence where you had small drops to start with, but now they have uh, connected to other small droplets, and now you have larger droplets. And that's still in the liquid, but um, they have changed in the nature of that dispersion. The goal of food preservation is to decrease microorganism growth, and that has a lot to do with the water content of the food, both the water activity and the availability of the water, whether it's free or bound. Think jello, you can't squeeze that water out of the jello. Foods do not support bacterial growth if they have a low water activity value, if it's below 0.85. Also, solutes will reduce the water activity via osmosis, which we will talk about now. So, with osmosis, which you probably already know this is where you have the movement of a solvent through a semi-permeable membrane toward a higher solute concentration, aiming to equalize solute levels across the membrane. Example, here you have in example 1, you have equal numbers of solute on either side of that semi-permeable wall. And in view 2, you've now added solute to one side, but not the other, which changes the concentration. And then you see in view 3, the water can flow both ways, but it's going to gravitate to equalize the concentration. So you see the water shifted more to side B to equalize the concentration. Let's talk about carbohydrates. We're talking about sugar, starches, and fibers. These are mostly derived from plants, although you can have a small amount of carbohydrate in muscle glycogen, which is where the body does store some carbohydrate, and also in milk, the lactose in the milk, the milk sugar. Some of the starchier vegetables would be carrots, potatoes, and beets, although all vegetables will have some carbohydrate. These are composed of carbon, hydrogen, and oxygen. Notice not nitrogen. You won't see nitrogen at play until you get to proteins, and that's the distinguishing factor. I love this diagram because it helps you remember the classification of the carbohydrates. You'll notice in food science, in almost every lecture, there will be some classification scheme that helps you understand what we're talking about. Notice that and look for that in the various lectures. So with carbohydrates, you're going to have monosaccharides, which are a single unit. You have disaccharides, which are two units joined together, and polysaccharides. Polysaccharides would be starch. Those are longer chain starches. You have amylose and amylopectin. And then you also have a little bit of starch in the glycogen, which is stored in the animal muscle. You have undigestible polysaccharides, such as which would be fiber. Um, and the types of undigestible fiber we're talking about would be cellulose, hemicellulose, pectin, gums, inulin, and others. Now let's go back to the monosaccharides. I don't know if you've already had human nutrition, but if you have, you know that we have to get our um, our food broken down to the smallest possible unit so it can be taken up through the bloodstream to the cells. And that's a whole process, and that's what you study in human nutrition is how that happens. But for food science, we just need to know that the simplest form here of these carbohydrates would be glucose, fructose, and galactose are your monosaccharides, 1 unit, 6 carbon atoms. Your ribose and arabinose we'll talk about also. Those are 5 carbon atoms. Now, your disaccharides are various combinations of your monosaccharides, and we'll talk about that in the next slide. Okay, so here is a figure 3-11 of your hexoses, your monosaccharides that we think about in the simplest forms of sugars, which would be your hexose here. You also have other forms, but we're not talking about those right now. We're talking about these hexoses. Glucose, which is predominant in the bloodstream, that is found in fruits and honey. Fructose is found in fruits and honey, and galactose is part of the lactose in milk. Okay, your pentoses or your 5 carbon sugars would be ribose and arabinose. The disaccharides will be seen here where you have 1 molecule of glucose and an additional molecule. So all 3 of these disaccharides have 1 molecule of glucose. So it's a glucose plus 1. I like to help students study that way. Glucose plus 1. They all have glucose. Now let's learn their plus 1s. So sucrose has fructose as a plus 1. That is going to be table sugar. Lactose has galactose as a plus 1, and that is going to be your milk sugar. And if you notice, galactose has lactose in the name. And then maltose has another glucose for a plus 1. So that's 2 glucose units. And that is found in beer. Think about malt liquor, cereal, and some infant formulas where you have 2 glucose molecules linked together. Your oligosaccharides are a smaller polysaccharide. Polysaccharides incorporate this category, but when they're smaller, like 3 to 10 monosaccharides, we call those oligosaccharides. And here's some. We have raffinose and stachyose found in dried beans. As you know, these aren't digested all that well by humans, and there's some flatulence involved. Well, there's a workaround for that. You can buy an enzyme. It's marketed as Beano. There are some generic forms, and that provides the enzyme to break down the carbohydrate there. Okay. And then you have fructooligosaccharides. These are found in asparagus, bananas, chicory, garlic, and onions, which act as prebiotics. Your polysaccharides, we're talking longer chain here, would be starch and glycogen. Starch is the stored form of energy that you find in plants, and that is digestible by humans. And glycogen is the storage form of energy for animals. And again, we do have some stored carbohydrate in the human body, and animals have it too in the muscle because we do store a little bit of carbohydrate there. It is digestible by humans. Another category of polysaccharides is fiber, which is also known as roughage or bulk. This is not digested by humans, so it helps gastric motility. It can bulk up the stool as long as the person is also consuming enough water for that to happen. This is found only in plant originated foods. You have soluble fiber and insoluble fiber. We will talk much more about that in the vegetable lecture. Also, you see cellulose, hemicellulose, and pectic substances. You have vegetable gums, inulin, lignin. Again, this will all come up in a future lecture. Let's talk a little more about starch. Here are the two forms. You have your amylose, which is a straight chain, and your amylopectin, which is a branch chain. You see here, that's a little cutout there. And most starch is going to consist of a mixture of amylose and amylopectin, which can change over time. For instance, bread can go stale, and you can revive it with heat just at least once. You can heat up a stale pastry and it will be uh, soft again. So you can't do that too many times. It won't work, but it will initially. If you notice on figure 3-15, this is a description here of glycogen. It's a sketch, and notice it's not that different than amylopectin, but it is different. When we're talking about fats, we're usually talking about solid fats at room temperature, such as um, you can see the the marbling in meat. If you can see it, it's white, or around the edges of a pork chop, that kind of solid fat. Or if it's room temperature and it's liquid, then that would be what we would call an oil. That's the differentiation. Sources of lipids would be high fat animal foods that could include meats, poultry, and dairy. For instance, poultry skin is fat. As I said, the white globs of fat in meat or around the edges would be fat. Plant sources of lipids would be nuts, seeds, avocados, olives, and coconut. There are some others, but those are the main ones. Types of fats would be the visible fat that you can see in meats and oils. The invisible fats would be very well marbled meat and a very tender steak where the fat is dispersed so well that you can't even really see it. That makes for a very tender steak or other cut of meat. Composition of lipids would be carbon, hydrogen, and oxygen. Now, lipids do not dissolve in water, but they will dissolve in some other solvents. Okay, the types and functions of lipids. Triglycerides, which you may be very well familiar with, especially if you've taken human nutrition, comprise about 95% of lipids, and they're made up of three fatty acids that are linked to a glycerol. You have phospholipids and sterols. The phospholipids are very much used as emulsifiers in food science. Sterols, these include cholesterol and plant sterols. Very difficult to get enough of in your diet, but if you do, it can reduce the risk of coronary heart disease. There are some margarines that are marketed as a plant sterol source, if you can see those in the dairy case. Fats are used to enhance food texture and flavor. Fats make foods tender and flavorful, and that's the draw. Think of ice cream. Now, we mentioned fatty acids a moment ago. And the way this works out is here you have your carbon chain. You've got hydrogen taking up all the available bonds. The carbon is saturated with hydrogen. Now you look to mono unsaturated. That will be one carbon bond where there is no hydrogen, and that would be a double bond. And when there's one, that's mono unsaturated. When there's more than one, that's polyunsaturated. Proteins are named from the Greek word proteus, meaning prime importance. We must have proteins. They're essential to life. The body can make some of them, but there are some that are essential amino acids, meaning they're essential to your diet because your body can't make them. Most plant proteins are going to be incomplete because they're missing some of the essential amino acids. Whereas if they have all of them, they're complete protein. We must have complete protein. And if you're going to use plants for protein, there are a couple that would qualify for complete protein. Thank goodness. There's soy, which you see tofu, and that's a choice a lot of vegetarians will use as a main dish. Quinoa, which is a grain that also is considered to be a complete protein, and amaranth. Those are the ones that are the exception from the rule. Proteins contain nitrogen atoms in addition to carbon, hydrogen, and oxygen, which is what differentiates them to be protein. The functions and uses of proteins in foods. We use proteins in food preparation. Again, there's several lectures that talk about this, but we use proteins for hydration, denaturation, coagulation, enzymatic reactions, buffering, and browning. But we will cover that extensively in the meats section. Proteins can act as binders, stabilizers, and thickeners. And also in bread making, we use proteins for the hydration needed to allow the dough to rise. When we get to the bread lecture, we'll learn that grains have differing amounts of protein, and that will tell you how hard the product is. So if you have hard wheat, you're going to have hard bread, like hard rolls. If you have soft wheat, you might have you might see that in cake flour where you have a very soft texture. This is a good classification slide. Like I mentioned, we classify everything in nutrition. Here's your essential amino acids here, your non-essential amino acids here, and then some other compounds that will get classified as amino acids. They're here. Now, back to your non-essential, some of the non-essential amino acids can be what we call conditionally essential if there's something missing that the body needs to form this amino acid. Okay. This is a great table, 3-5, that gives you some examples of how enzymes are used by the food industry to test for food quality. I'll pause here for a minute and give you a chance to read across. The test for food quality might be that it was heated properly, freezing and thawing quality, especially if it was thawed out and then refrozen, bacterial contamination, maturity of the food, freshness, sprouting, and color. These are some examples. Have you ever noticed that some of your fruits turn brown if they're exposed to oxygen, but not all of them do? Well, in order for that enzymatic browning to happen, there needs to be oxygen and an enzyme and a phenolic compound. Thinking about enzymatic browning, here is a discussion activity. If you are in the classroom, your professor may decide to pause the video for the discussion to take place. If you are viewing the video not in a classroom setting, you may want to pause so that you can think through these questions. One would be to explain why only some fruits and vegetables are affected by enzymatic browning. And the second one is to discuss the reasons for food fortification and why we must carefully control this process. Okay, here's some notes to go with the questions. I am not going to read this. I will just suggest that you pause the video if you want to check your answers. And here's the second part of that. Okay, moving on to vitamins and minerals. Vitamins and minerals are also important to think about in food science. One thing that you need to know about some of the foods is that they're enriched, where some of the nutrients that were lost in processing are replaced, as opposed to fortification, where you're adding nutrients that were never present to start with. Also, vitamins serve as antioxidants, some of them. And then for sodium, the mineral, we use that in food preservation, also in flavoring. Another classification showing you the water soluble versus fat soluble vitamins, and then macro minerals versus micro minerals. Here's an example of a vitamin E serving as an antioxidant. So here you have an oxygen-free radical, and these are your fatty acids in this diagram, and you see this chain reaction. Vitamin E can come in and wall that off and stop that reaction. Food additives, we do need to discuss food additives for a bit. A food additive definition here is that any substance, the intended use of which results or may result in, directly or indirectly, becoming a component or otherwise affecting the characteristics of any food. Sometimes we use food additives for improving the appeal of foods, the flavor, smell, texture, or color. We also use food additives to extend storage life, to maximize performance, and protect nutrient value. We have a critical thinking scenario here, which again, I'm going to pause for a moment, let you read this, and also to give your professor a chance to pause the video, or for you to pause your own video to think about this question. How might the benefits of food additives be balanced with potential risks to the public? Okay, and I'm about to advance to the notes on that to compare notes with what you wrote down or thought about. Okay, and again, I won't read this. This is for your information to compare the notes with what you wrote down. Now, here are some substances that naturally occur in foods that are non-nutritive, meaning they're not going to provide calories. They're not providing any of the classes of nutrients. These are chemicals in plants. Here are some concrete examples of each of those categories where you can see names of food items that fall in the categories. And in summary, we covered the objectives for the lecture. We explained the compositions and functions of the 6 nutrient groups. We gave examples of the role of water in food. We described the chemical structure of carbohydrates, lipids, and proteins. We provided food sources and functions of carbohydrates, lipids, and protein. We listed the main vitamins and minerals found in foods, and we defined several non-nutritive substances found in food, especially food additives. Thank you for your attention. This concludes the lecture.